Hi everyone. So this question was sent to me by one of my viewers, Akshat, and it's a really interesting one, but I couldn't actually work out how to solve it with classical geometry. I had to use analytic geometry with a bit of help from the computer. So this episode might be just a little intro to how we can use computers to help us with mathematics. So if you'd like to have a go at this one yourself, then pause the video here. Otherwise, keep watching. Okay, so let's start by trying to draw a diagram from this information. So we've got this isosceles trapezoid, or I would say trapezium, being from Australia. A, B, C, D, and the isosceles bit just means that that's the same length as that. And then we've got E is the midpoint of AC. And we've got a circle passing through A, B, and E. That one's called omega. And we've got a circle through D, E, and C. And that one, well, we should really call that big omega because it's not standing for the ohm unit here. It's just a capital omega. And then we have a tangent to big omega through D and a tangent to little omega through A, and they meet at P, and then we have to prove that PE is tangents to big omega, and I haven't drawn this very well. So as I kept working on this problem, I got quite fed up with drawing it by hand because it got very complicated, lines everywhere, and so the first way that computers are going to help us with this problem is with generating a nice, neat diagram for this question. So I favor meta posts for creating diagrams, and that's what you see here. This is the meta post source code for creating this. And this was really useful because, first of all, the diagram's really neat. It's much easier to see things. And also I could play around with stuff like, I was wondering, for example, was it important that E is the midpoint of AC? So we could try that out now. We can try maybe moving E a bit closer to A, and then we'll see if this still looks like a tangent line. So let me just recompile this, and then you can see now it's no longer tangent. It's going to cut into the circle. So that's really useful. To have this neat computer-generated diagram, because you can actually sort of test out various guesses that you have. Now, one of the first things that I tried to do was, how could we use the fact that PD is tangent to big omega and AP is tangent to little omega? Like, what do we do with that information? Well, what I was thinking is, we can use the theorem that the angle between tangent and chord, so this angle here, equals the angle in the alternate segment. So this angle here is the same as this one. And for this circle, it's that angle there is the same as that one. So that's really useful because then that allows us to take out the circles from the diagram, and they are really visually complicating things a lot. So that's very useful. The next thing we might think about is how we're going to prove that PE is tangent to big omega. So like, what would be the step right before the end? Like, what are we aiming for? So what I was thinking is, if this is the center of big omega, then what we'll have, if PE is tangent, then this will be a right angle. So these two triangles will actually be congruent because they've got, that side is the radius, so those two are equal. This one's common, and we've got the right angle there, so they'll definitely be congruent. So I was thinking how we could get to there is if we can prove that that length is the same as that length, because then we could show that they're congruent, and then that would prove that that's a right angle, and therefore that's a tangent. So how could we prove that that's equal to that? Well, in this triangle, if we can show that that angle is the same as that one, then that means that this one is isosceles. So that would equal that. So I'm going to talk more about problem-solving techniques in a future video. I was going to make one that's called What Video Games Taught Me About Mathematics, which is just all about general problem-solving strategies. But so what you want to be doing is sort of, from the information you have, you want to be thinking, what can I do with this information? So you've got all these facts, so you're trying to work out where you can go from there, but you're also looking at where you want to get to and how you could get there. So it's a bit like, here's where you're starting, here's where you want to end up, and you want to sort of look at all the paths coming out of there and all the paths going into here and try to make them link up eventually, hopefully. So yeah, so the paths ending in, what we want to prove, one possible way to do it would be showing that this angle is the same as that one, because then that shows that that equals that, and then that would show that these two triangles are congruent, and therefore that's a right angle, and so we've got a tangent. So that was my plan of attack for this question. Okay, so I'm just going to lose the circles from the diagram because we actually don't need them anymore. Now that we know that that angle is the same as that one, and that one's the same as that one, and we know where we're going, we actually don't need the circles. So that simplifies the diagram a lot. So I tried to solve this with classical geometry, but I didn't really get anywhere. I couldn't think of any good way to use the fact that E is the midpoint of AC, like that length is the same as that one. So instead we're going to use analytic geometry. So that means assigning coordinates to the points and sort of using algebra to solve it. So first we can decide where to put the origin. So you can put it anywhere. I decided to put it at E because that's going to simplify things a lot. So we could say B has coordinates, let's call them xb, yb, whatever that is. And then C can be at xc, and because that distance is going to be the same as that one, because that's the midpoint, this is just going to be negative yb. Now for A, we've got that distance is the same as that one, again because of the midpoint. So this will be at negative xc, but same y coordinate as B. So yb. And then for D, I was thinking like, because it's an isosceles trapezium, or trapezoid, that distance, like from B out to C, is going to be the same as from A to D. So like that is going to be xc minus xb. And then, so the x-coordinate of D is going to be the x-coordinate of A, so negative xc, and then minus that because we're going to the left. And then the y-coordinate is going to be negative yb, and then this simplifies down to, let's say, xb minus 2xc. All right, and then we can start thinking about how we're going to find the coordinates of P. So what I was thinking was we can use, okay, so first we want to work out the slope of this. So that's going to be the tangent of whatever, tan of whatever that angle is. So if you, let's call that alpha and that beta. So we want tan of alpha plus beta. That's going to give us the slope of that line so that we can work out the equation of the line so that we can have the equation of that one as well and then work out the intersection point, and that'll tell us the coordinates of P. So if we want tan alpha plus beta, what we can do is use the angle sum formula for tan. So tan alpha plus tan beta on 1 minus tan alpha tan beta. Okay, so let's see if we can work out tan alpha. Now, because that's the same as that one, so this is also alpha, and we've got the coordinates of C, you can imagine like a little triangle here where that side is YB and this side is XC. So tan alpha will be YB over XC. And we've got tan beta as well. We can work that out. That's going to be this, YB over this distance, which is going to be the negative of this, because this is already negative. So that's going to be like 2xc minus xb. So we can work out the slope of that line using this. Now, here's where I'm going to have to start using the computer to help me with the algebraic, because it gets a little bit complicated. Now, when I was in university, there's various different computer algebra systems. So at my university, it was that physicists used Mathematica, engineers used MATLAB, and mathematicians used Maple. So that was a bit confusing if you had classes in all the different departments, because then you'd have to learn all three different computer algebra systems. But I'm actually not going to use any of those today, because they're all ones that you have to pay for, and I want to keep this sort of accessible to everyone if, you know, whoever's watching wants to try out this stuff for themselves. So I'm going to use Sage, which is a free open source computer algebra system. So you can try it out for yourself if you want. All right, I'm just going to boot up Sage, and then we'll see what we can do. Now, the first thing we need to do is tell it what the variables are. So I'm just telling it that xy, yb, xb, and xc are variables. So now let's define, we could define tan alpha as yb on xc, and let's tell it what xd is. So the x coordinate at d, which is that xb minus 2 times xc. And then we can define tan beta as yb on, it was negative xd. Okay, so now we can define the slope of dp using that formula. So tan alpha plus tan beta divided by 1 minus tan alpha times tan beta. And now we can define an equation for this line. So I'm going to say equation 1, it'll be like, you know, y minus y1 equals mx minus x1. So y minus this y coordinate, so that's going to be y plus yb equals, we have to use a double equals sign. The difference between these is that this one is assigning whatever's over here to equation 1, whereas this one isn't an assignment equals, it's a, like, stating a fact, stating an equation, not defining a variable. It's a distinction in computer programming. So okay, so y plus yb is mdp times x minus xd. So that's our first equation. And now we can think about the equation of this line. So let's call this gamma. So that's gamma as well. And this angle is actually an alternate angle with that one because of the parallel lines, so that's also alpha. So we can work out the slope of this by working out the tangents of these angles. So let's think about tan of gamma. If you imagine a little triangle here, that height would be yb, and that is xb. So tan gamma is yb on xb. And then we can say the slope of AP is going to be, well, it's going to be the negative of the tan of this angle, because it's going sort of down this way rather than going up. So it's going to be negative tan alpha plus tan gamma on 1 minus tan alpha times tan gamma. Okay, so we can actually have a look at that if you want. I didn't want to do all this by hand, but it just got a little bit messy, so I mean, it's doable, but it was a bit annoying. Okay, so now we can define equation 2 as y minus the y coordinate here. So y minus yb equals the slope of AP times x minus the x coordinate here. So that's going to be x plus xc. Okay, and now I can just tell it to solve those equations simultaneously. So say the solution equals solve equation 1 and equation 2 for x and y. Okay, so that's the solution. You can see there's only one solution, which you would expect. You wouldn't expect to have two intersection points with straight lines. Now, I want to save these as the coordinates of P. So I'm going to say xp is solution 0, 0. So this first 0 is just saying take the first solution. There's only one solution, so. And then this 0 is saying take the first element of that. So that's referring to all of this. And then I just want the right-hand side of that. I don't want xp to be that whole equation. So I'm going to say that dot RHS, right-hand side. And then yp is going to be the second part of that. So this bit, right-hand side of that. Okay, and then we can think about how we're going to work out this angle. Remember that I want to show that this angle is the same as that one. So what I might do is imagine a horizontal line going across there. And then this angle, because this is parallel to that, that's going to be the same as that one. So that's beta. And then maybe we can call this one delta and think about what tan delta is going to be. So if you look at this triangle here, that height is going to be the y coordinate of P. And that, because the x coordinate of P is negative, like it's to the left of the origin, that's going to be, that distance is going to be negative xp. So we could say that tan delta is yp on negative xp. And then we can define tan of angle DEP is going to be, so just this formula again with delta and beta. Okay, so that is going to be tan alpha, no, not tan alpha, tan delta plus tan beta on 1 minus tan delta times tan beta. Okay, let's see what that makes. So that's a bit complicated. I'm just going to tell it to simplify this. Okay, YB on XC. Now that's interesting because tan alpha was YB on XC. So that shows that these two angles are actually the same. I mean, technically they could be, like angle DEP could be that plus 180 degrees, but that doesn't really make sense. So that shows that they're the same angle. So then we can go, okay, that triangle is the same as, is congruent with that triangle, and therefore that's going to be a right angle. Yeah, so that's the proof. Alright, I hope this was useful and interesting to you. I'm going to put some links in the description below for where you can download MetaPost and Sage and get more information on them if you're interested. So check those out. And this probably wasn't the most elegant proof of this problem. So if you've got a better idea of how to solve it, then let me know in the comments. And don't forget to like and subscribe.